go. All right, so good. So good afternoon, everyone, and welcome to our class this afternoon. It is being recorded. Again, because once I'm watching full screen here, I can't see, I have no way of monitoring the chat. So when you want to ask questions, just politely interrupt, get my attention, and I'll answer the question as we go along. Okay? All right. So where we started last week, we started to look, our first topic was regulated power supplies. Of course, let me know if you're hearing me properly or if there's any break in the transmission for any reason. So we started with regulated power supplies. And just to remind everyone, these were the sort of sections of the regulated power supply unit that we were looking at. And we covered last week, we covered the transformer section, right? We spoke about that depending on what sort of voltage you want. Remember what it's doing is taking the line voltage in, which typically for us is 120 volts, and we said plus or minus 6%, right? That was here. And you can now converting that into some low voltage. The amount, the value of this low voltage here is determined by what DC voltage you want coming out. So you choose a transformer that gives you that voltage. Remember that it's a step down here, and then it's rectified. But what you want is depending on when you either do half wave or full wave rectification. This particular one is, of course, a full wave rectified signal DC. And then once you put the filter here, remember the filter was a large electrolytic capacitor, and you got the regulated DC voltage coming out. Typically, what you want is that this voltage here determines what sort of AC voltage you want on the secondary of the transformer, right? Once you rectify it, you remember whatever the RMS coming out here, you have the RMS by √2 giving you the peak value. So at least you will have an idea what the peak value is here. So, and you normally try to make sure that that may be at least 2 to 3 volts higher than whatever the final usable voltage of the unregulated supply is. So we stopped here, and we saw in the class example that we spoke about, that the class example was something to charge a car battery. So we wanted to charge a 12-volt car battery, and we said, okay, we would use typically, let's say, about 14 volts to charge. And we worked out some simple calculations for a half wave and a full wave unregulated DC supply. And we got various capacitor values and so on, and we spoke about that. We spoke about the rectifier here. If it's half wave, we're using 1 diode. If it's full wave, you can use 2 diodes or you can use 4. Right? And there were some things that we spoke about in terms of how much load the rectifier itself had to take before it would break down, something called the peak inverse voltage and so on. But this wasn't, we saw that at least for the application of a car battery charger, the unregulated supply was usable. But remember the regulation, the output voltage that you're looking at is really something looking like this. Right, so there's an average value, but there's a big up and down variation on it. And the more load you put on the more load or current that you take from the unregulated supply is the more this variation becomes. And we call that particular variation, the up-down variation, the ripple. Okay? So what we want to do now is to see if we could improve on that situation here. One way of improving on the ripple, of course, was to use this filter here, which was a capacitor, was to use a large or larger capacitors. But we spoke about that. Large capacitors, one, they're expensive. Two, they take a lot of current to charge them up initially. So then you're going back to how much current your rectifier and your transformer and so on can supply. Okay, and we spoke about all of that. So now let's have a look at something, hopefully, that will help us to improve the situation. Just to summarize, the sort of issues that the unregulated power supply had was first that the DC output voltage decreased and the AC ripple increased or increases as the load current increases. So the more current you tend to pull from the unregulated supply, the more this up and down variation is going to occur. And these were the values of these are the equation for the half wave and the full wave to calculate the value of the capacitor. And remember this, that the DC value, if you're looking at the voltage and it's doing you something like this, the DC value, which is through the middle there, right, is the peak value. This is V peak. This here, this distance here is delta V. So delta V over 2. Delta V over 2 is about halfway here. So V peak minus delta V over 2 is going to give you this voltage here, which is a DC voltage. Of course, the bigger this gets, the bigger delta V gets, is the more variation. Hello? Somebody ask a question? Okay. The bigger delta V, which is the ripple gets, is the more sort of fluctuation you're going to get on it. And of course, the lower your DC voltage is going to be, because delta V over 2 is going to be a larger number. So, and then the other thing now is the line voltage. If the line voltage changes, the output voltage is going to change. Remember this one, if this 120 volt changes to 120 plus 6 volts, plus 6%. So let's say we go up to about 128 volts here. Whatever we have on the transformer is going to go up, and consequently, all of this is going to go up. If this went down to the lowest, which is about 108 volts, then VDC is going to go down as a consequence of that as well. So your voltage really is at the mercy of what happens on the input line coming in. Okay, so those are two things. So what we want to do now is to stabilize that by adding a bit of circuitry called a voltage regulator. And once we do that now, we have converted the whole thing into something called a regulated power supply. And the function of that is to maintain a constant output voltage. There's a key, to maintain or to try to maintain a constant output voltage under conditions where your load current is changing and the line current is changing. All right? It looks like something challenging, but within reason, this is one of the things that we do in engineering, is that we take a large problem and we break it down and we constrain it into a zone that we could work with. All right? So let's see how to do that. Of course, if you have any questions at any point, just feel free to let me know. I can't read the chat. So two types of voltage regulators we have. We have one called the shunt regulator, where you put something in parallel with the load. And the load, remember, anytime we're talking about a load here, we're talking basically about a resistive. Right? So at the end of the power supply, if you just skip back to here, the load here is going to be a resistor. Okay, so this is my load here. So once what we're talking about here is that if I put the regulator in parallel with the load, I have a shunt regulator. And then if I put the regulator or whatever is the particular bit of circuitry that I'm using in series with the load, then I have a series regulator. And we use both of them, and actually it's a combination of both of them to get the sort of performance that we want, right? And then of course we kind of, in order to compare apples with apples, we have a set of sort of tests that you talk about, one called the ripple factor, one called the load regulation, and one called the line regulation. And you will see these specifications appearing from time to time. as it would imply, the ripple factor, remember, you have the output, and the output is doing something like this, right? So the ripple factor has to do with, first off, this is the DC here, and this is the peak-to-peak ripple here. Okay, so you get these sort of measurements by, of course, as we say, looking at it on on an oscilloscope, and the ripple factor is the ratio of the peak-to-peak ripple over the average value of the DC. And of course, you want that to be as low as possible. Ideally, what you want is that the ripple factor, your DC should be looking like this all the time, right? So they basically, the ripple factor is 0. And we could get fairly close to 0 if we design whatever we're doing cautiously or carefully. The other one is the load regulation. And the load regulation now has to do with how much the output voltage changes as we change the current. So if you go back here a little bit, this is what my output is looking like, the red line, right? Ideally, what I want is to get the output voltage to look like this. So if I have some value at no load means no current. Remember, the load is a resistive load. So no load means I don't have any current being taken from the power supply and it's giving me some voltage. Put full load on the power supply, right? Meaning that it's supplying the maximum current I've designed it to supply. And then you express that as a percentage of the full load, what do you call it, DC value. Ideally, these two are supposed to be equal. So if they're equal, the load regulation should be close to 0. And the line regulation, well, as the name implies, is how much the output changes every time the input changes. All right, again, ideally, we want that to be 0 as well, that the input could go up and down as much as it likes within reason, but the output should stay on whatever I set it. So like when you go in the lab and you pull up one of the lab power supplies and you set it to 15 volts, and you're working on a circuit and you have a 15 volt supply coming out of the power supply, regardless of what the input voltage, the line voltage to the building is doing, let's say it is going up and down and so on, you're not supposed to see that. Your 15 volts should remain 15 volts almost without changing, right? As we say, nothing in engineering is perfect. So for good regulators, you're looking at things like 0.01%, which is really a small amount. So you're talking about, like with 15 volts for argument's sake, just to take that example, that you're varying by millivolts, all right? So let's see how the regulators work and discuss it a bit. So the first one, the simplest sort of regulator is the shunt regulator. And what we do in that is that we take a device called a Zener diode and we put it in parallel with the load. So this is a load here. This here is the unregulated supply. So those first 3 blocks that we had in the sections, right? The transformer, the rectifier, and the filter. Up to this point now, we're putting the voltage here. And what we're doing now is that we're adding 2 elements to it, a resistor and a Zener diode, and we are supplying our load from the output of the Zener. Now, if you remember from the electronics from last time, that the Zener diode, it's a diode, but it's designed to work in the reverse bias range. When it's forward bias, it works like a conventional diode. It conducts once the anode to cathode voltage exceeds about 0.7 volts, then it will conduct. But that's not the useful part of it. The useful part of it for us is when you reverse bias it. When you reverse bias it, very carefully, the voltage across here, which I will call VZ, once you reverse bias the Zener diode and you supply it with a certain amount of current to start it conducting, right, which is called the breakdown region. So you you reverse biasing it, and then when you reach a certain voltage now, the Zener starts to conduct. And it will conduct, and it takes some current. It's operating in the breakdown region now. And a very constant voltage now appears across the Zener diode. And it stays so once you do not pass more current than the diode can handle. The diode has a range. It needs a minimum amount of current to kick in. So as you start to reverse bias, remember you have the cathode here, so you're putting a voltage at this point. As you start to get the voltage bigger and bigger and bigger, eventually current starts to go this direction. That is IZ min. So the Zener diode is now operating. Once it gets a current greater than IZ min, then a very constant voltage VZ appears across the Zener. And you can keep increasing the current until you reach there's a maximum now that the Zener diode can handle. If you go beyond that, you burn out the device, and then you have to go and get another one, right? So ideally, you want the system to at least give you IZ min for it to work, and you cater for the worst case. Whatever happens, you don't want it to ever get past IZ maximum. Everybody with me? At least give me a shout every so often, because I can't see the chat. Everybody following?
Yes.
Oh, that was a sleepy yes, but anyway, at least you're up. Right. So here's where we just explained that a little bit. So the Zener, it starts, as soon as you exceed IZ min, it starts. Less than that, it stops and it just switches off. And at IZ max, the thing is going to burn out. So how do we design using that? Well, the first thing we need to do is that the current passing through, notice how we have it. We have the load. This is what I want to supply power to. Okay, RL. So we need to make sure first off that the Zener gets at least IZ min to work. And we need to ensure that this load gets IL to operate. Okay, so whatever current is passing through this resistor is IZ at least min, okay, plus IL, right? So that's the current coming through from the unregulated supply here. It's IZ at least min for this thing to start working, and whatever the load current is. And what happens here? So now look at what we have to be a little bit aware of. As the load current increases, the current drawn from the unregulated supply increases. What that does is that causes the input voltage to drop. So as I start to get IL going up, as IL goes up, the more current I take here, VI is going to drop. Fair enough? So VI is going to drop as IL goes larger. And what we want to ensure is that when I'm taking the maximum current here of my load, whatever the maximum current that I'm taking here, that and the current that I'm taking from the unregulated supply, at least I am able to supply IZ min, which is what I was saying. So the current coming to the supply must be equal to supply IZ min plus the load current, or the other way around, because we want to see how we're working with the Zener itself. The current coming from the unregulated supply minus the load current must be at least equal to IZ min. If it is not, then of course the Zener diode not going to work. Okay. And then if you juggle it around here and look at it, remember I told you that most of the circuitry here is straight Ohm's law. This current here, I, let's get a different color here. This current I remember this point here is at VZ, right? The Zener diode. Once the Zener diode is conducting, here is held at a constant voltage. So the current through this resistor will be V in, or let me use the what I have here, VI. Oops. Right. So VI minus VZ over R. So the current is equal to that, right? And we know that because we're dealing with we're catering for the maximum current that this load will want, that this is really in fact VI min, right? The more current you take from that, the lower this goes. Remember, this is doing this thing here. So the more current you take, no current, the voltage is here. At maximum current, the voltage is at VI min here, right? So this now, and we know that this current I is comprised of the Zener diode plus IL. And in this case, IL max. So we have a constraint that this now, the Zener diode current must be at its minimum for it to work. So between the two equations here, we now have a little expression that we could calculate the value of the resistor. And it's simple. So whatever is the minimum unregulated voltage minus the Zener, and the difference between whatever the maximum load current is and the Zener current. And we have everything that we need now to design the circuit. So let's take an example. Here's one. I have an unregulated supply that the minimum voltage is 16 and the maximum voltage is 20. This is DC. And I want a regulated supply that is going to give me 10 volts DC and supply a current of 10 milliamps. So you want a 10 volt DC, so you're going to choose a 10 volt Zener diode. You need to determine the current from the IZ min for the Zener. Usually, and we'll talk about that a little bit later on, you typically would go to the data sheet for it. So you just pick a Zener diode and choose some arbitrary value. But let's assume that this Zener diode needs a minimum of 5 milliamps to turn on. The load current, I load max, we said is 10 milliamps from the problem. So this, whatever this thing is here, once 10 milliamps, the Zener diode needs another 5 milliamps to work. Right? So that IL plus IZ minimum is 5 milliamps, I load max is 10. So we have 15 milliamps below here. Right? What is VI minimum? Well, they told us here that the minimum voltage is 16 and the Zener diode is 10. So this is 16 volts here minus 10. So if you do all of that, you now have that the resistor here, this R, which is a current, is limiting the current in the power supply, is 400 ohms. All right, so we're almost there. We just simply put a 400 ohm resistor, a 10 volt Zener diode, connect it up here. I have 16 to 20 volts DC here, and I'm going to get 10 volts at 10 milliamps here. The last thing we need to do, however, is to make sure that the Zener diode can handle the worst case. You remember, we designed for IZ min to make sure that it turns on. But what we want is, while it's working, that it never goes past IZ max. So when does the maximum current flow through the Zener? The maximum current flows when this load is disconnected. If I was to suddenly disconnect this load, it means IL is 0. If IL is 0, V in is going to jump up to 20 volts. So at that point in time, what you have is now this. You have 20 volts here. You have a 400 ohm resistor, and you have the 10 volt Zener. All that current is now going to pass through the Zener because you have no load. Remember, the load is connected here, right? But you have nothing connected now. So the current passes through the Zener. And what current is that? It's going to be 20 minus, it's going to be 20 minus 10 over 400 amps, whatever that is. Right, so that's 10 over 400, that's about 25 milliamps. Right, so at no load now, the Zener, so this is IZ max, right? It's 25 milliamps. IZ min was 5 milliamps. IZ max is 25 milliamps. Usually what you do is to go and choose a diode that can handle the power. So this is, remember, this is now passing. This is 10 volts across here, and it is passing 25 milliamps. So how much power is it dissipating? 25 milliamps by 10 volts. In other words, a quarter watt, right? So this is 0.25 of a watt. For safety, in a situation like this, what you would do is that you would go in stores or you would go online, wherever you're buying it, and you would choose a Zener diode that has a little bit more room to maneuver, a half watt, 0.5 watt. Make sense? Yeah, no, maybe? You're following what I'm saying?
Following.
Yes? Any questions?
No question.
Okay, good. As I say, I can't read the chat all the time. So unless somebody says something, I wouldn't know what's happening. Right. So a little bit of a comment here on this. Remember, this is a shunt regulator, the Zener regulator. A shunt regulator is useful for low power applications. So typically, if you only want to supply a few watts, or in other words, a few milliamps, a few maybe tens of milliamps, and so on, right? The main issue with that is that because when you're not taking any current, the Zener has to take basically the full full load of the unregulated voltage coming at it. All right. The other little thing you have to be careful with too is that the Zener has a diode. Sorry, the Zener diode has a resistance. When it's on, it behaves, because it's conducting, it behaves as a small resistor, somewhere in the 5 to 100 ohm, depending on the type of device. If you consider that now, the Zener is, this is the Zener diode here, but when it's working, it's behaving like a low resistance, somewhere between 5 to 100 ohms. Now, this is in parallel with the load, right? So one of the things that you have to be careful with is that if you remember, when you have two resistors in parallel, if you remember from your circuitry, if I have two resistors in parallel, RA and RB, if RA is less than RB, right, the parallel combination of this is going to be less than RA. Remember that? When you put two resistors in parallel, the result of the parallel combination is always less than the smaller of the two resistances. Or in fact, whenever you parallel any set of resistances, the value is going to be less than the smallest one. So if I put this diode in parallel with the load, and the load is what do you call it? Is considerably, is about the same size, I should say. If the load is small, such that this value here and this value are about the same, what you're going to do now is that the load, the Zener, most of the Zener current now is going to be going to the load, at least half of it. Just think, if this R was RD for argument's sake, then whatever current is going here is also going to go across here. What you really want is for the load RL to be a lot bigger than the Zener diode. Okay, so that most of the voltage that you have here, most of the Zener has its own current, but then most of the voltage across here is being provided to the load. Okay, if you check your slide, you're going to see a little mistake. This is why I put note here. The slide had R instead of RL. Right, so on slide 18 in this handout, it should be that if RD is much less than RL, meaning the load resistor, then the regulation, which is the variation of the output, the voltage on the output over the voltage on the input is a lot better. Okay, so let's make that change. I had R, for some reason, when I was transcribing it, I had R here. All right. The thing still has a little problem. I mean, the Zener diode could only supply so much current, a few milliamps. So what we want to do now is to see if we can beef it up a little bit. So let's have a look at this particular circuit here. What I've done is that we take the Zener here. Remember, this is the shunt regulator here, right? So this is my shunt because it is in parallel with the load. And what I've done now is to add a transistor in series with the load. So this one has both shunt, and we're now introducing a simple series regulator here. Now, how does that help us? Well, let's have a look at how this particular thing works. Right? Once this is operating, everybody looking at the circuit here now, remember, once we turn on the Zener, here, this point is a nice constant VZ. For this transistor to turn on, this voltage has to be what? Typically what? Anybody, just to let me know that you're 0.7, right? So the base has to be bigger than the emitter by 0.7 volts. So the output voltage is the Zener. If you look at it here, that the output voltage plus this, whatever this is, plus 0.7 is what the Zener voltage is. In other words, the Zener voltage has to be bigger than the output voltage by at least 0.7 volts. Okay? And then the other thing, if you remember from your transistor theory, that the base current here, whatever current is flowing in the collector here is HFE times IB. Now, HFE typically is like 100. You have to check the spec for the particular transistor. And then the other thing, we normally make the assumption that IE, which is the current here, is almost the same as IC. Right? All of that is just simple revision on how the thing works. So let's see how this helps us, right? So we're taking a single transistor and we supplying it with a Zener diode. The Zener diode is capable of delivering 12 volts at 100 milliamps. And let's see what the actual power supply will look like. So the first thing is that if the Zener diode, if the output voltage that we require, the output voltage of the power supply is 12 volts. And this is I load, right? So 12 volts at 100 milliamps. If here is 12 volts, and here is 0.7, then the Zener, what we need at this point in time is at least 12.7 volts. Okay? You're not going to get a 12.7 volts diode, Zener. You have to go and buy, or you have to look at it in the spec sheets. And I've just put in some things here because you'll go and just check these things as a little bit of homework and just getting familiar with it. The closest value you're going to get to Zener, 12.7 volts Zener is 13. So you have a choice. You will get 12 volts, you'll get 13 volts. If you pick a 12 volt Zener, it means the output is going to be 11.3. If you pick a 13 volt, the output is going to be 0.7 less than 13, right? So you're going to get what about 12.3, right? So you're kind of in the ballpark here. The input voltage here, typically we said, should be about 3 volts to bias the transistor properly. Whatever we want here should be about 3 volts more than that. So you want about 3 volts unregulated. So if you want 3 volts unregulated, right? Remember the unregulated voltage here. If I'm using a half wave rectifier, right, it's going to give me this kind of behavior coming here. So you want at least 15 volts coming here. And then you go back now to the transformer. So if you want 15 volts about coming here, then the RMS coming out should be about 21 volts. Or the peak volts coming. If you have 15 volts here, then the peak volt coming out of the unregulated thing will be about √2 that, which is about 21 volts. All right. So unregulated, no load, you should get up to about 21 volts here. You choose a ripple. So you decide what you want as a ripple value. You pick something. If you pick the ripple voltage, then you could go back to those little equations that we discussed last week, and you could calculate a capacitor, which is 1667 microfarads, which is strange. So you go to the closest available value, which is typically 2200. All right. So this side here would have my 15 volt transformer, which is giving me 21 volts peak DC, right? 1 volt ripple, and the capacitor is about 2200 microfarads, right? So that's coming in here. We have a 13 volt Zener here.
Yeah. 15 volts instead of 13 volts.
Sorry?
What is the reason why you're choosing 15 volts instead of 13 volts?
Okay. The power supply, remember the power supply is supposed to be a 12 volt power supply, right? That's what you're trying to get at the end. For transistor operation, if I want 12 volts here, what 12 volts is the output of the transistor, what I want on the collector of the transistor, there's a simple emitter follower. What I want on the collector of the transistor to make sure that it's biased properly is about 3 volts more than that. So I want 13 volts, at least something bigger than 3 volts more than the 12 volts. So I want about 15 volts here. Yeah? Okay?
Yeah.
Right. I was saying, okay, so if I want 15 volts here, if I take a transformer that has a 15 volt AC secondary, right? So the transformer, and I'm getting 15 volts AC coming out of the transformer. A 15 volt transformer will give me at least 21 volts peak coming out here unregulated, which is more than 15. So I could use that. I could use a 12 volt transformer if you want. 12 volts will give me 12√2, right? Which is what, about 16 point something volts. We worked out last time about 16, almost 17 volts, right? So you can play around with it. I just chose a 15 volt transformer here. So you could put this. This is the transformer voltage, right? Fair enough?
Yeah.
Right? Good. So what do we have? We have 21 volts here with a 1 volt peak to peak ripple, meaning that the maximum is 21, or the minimum is 20. Oh, go back here. The maximum is 21, the minimum is 20. So we now we have some things to calculate. The only thing we really have to get next is what value is this and what kind of transistor to use here. Like we did in the previous thing, the Zener has a IZ min that it needs. If you go to the particular spec for the Zener, you will find that the Zener, this particular one, needs about 5 milliamps to operate. Right? So if it needs 5 milliamps to operate, and we have 21 volts here, So 21, this needs 5 milliamps, and here's 13 volts. We could calculate the value of R. Yeah? Fair enough? Yeah, no, maybe? Everybody following? Good. So we calculate the value of R. R is 1.6K. What about the transistor now? So let's see how we figure out what to do with the transistor. The transistor itself, we have 12.3 volts here. The load current of this is 10 milliamps, right? It's 10 or 100? 100, sorry. 100 milliamps. So 100 milliamps. So that the transistor has to supply 100 milliamps coming through here. At 100 milliamps, remember what we said, at no load, you have 21 volts DC here. At full load, you have 20, because that's what we designed the thing to do. So at full load, we have 20 volts here, and we have 12.3 volts here. So there's a drop across the transistor of 7.7 volts. And how much current is the transistor carrying? 100 milliamps. So how much power is the transistor dissipating? 100 milliamps by 7.7 volts, or about 0.7 watts. So what you would want to do now is that the transistor you would get, you typically want, if it's 0.77 watts that it has to get rid of, you need a transistor that probably could handle about a watt minimum. All right? I just put one here for you to go and have a look at in a company called DigiKey, so you could kind of get an idea how transistor specs are. Transistors are not like you just go into the stores and you ask Brian or whoever it is, here now, I want a transistor to handle 20 volts and give me 100 milliamps. You're going to have to spec it out, okay? And what's the base current here? If the transistor current, emitter current, meaning that the collector current is also about 100 milliamps, what is the base current here? It's going to be 100 divided by whatever is HFE for our transistor. You're going to go to the transistor data sheet, and if you look it up, you're going to see that HFE is about 100. So that the base current here is just 1 milliamp. Right? So that the Zener, unlike the previous case, where when you have the Zener alone in the circuit, the Zener has to supply all of the load current. In this case, the only current that the Zener has to supply is the base current for this transistor, which is a very minuscule 1 milliamp. The transistor is doing everything else. Because of the current gain of the transistor is able to supply 100 milliamps, right? We wanted the thing to supply 12 volts, well, we're getting 12.3, and we'll talk about that in a little while. And the transistor now is able to dissipate 1 watt, which means it could go a little bit above 100 milliamps here. Right? So we know starting to get something a little bit more useful. This is almost like the kind of, like the little adapters that you could plug into the wall to power some small circuitry or to charge a cell phone and that kind of thing. It still has some problems on it, but because of it now, it is able now to give us a very nice 12 volts. Remember, the input here is varying between 21 and 20 DC. All right, so that's a 1 volt ripple here. The output is fairly constant at 12.3 volts at up to 100 milliamps. Right, and if even you reduce this to 0, it just means that the current coming, if you reduce this to 0, it just means that the Zener will not have to supply anything. The Zener is still on because this resistor is making sure that I, Z, min is always supplied. So we have a nice constant 13 volts here, even at no load. And here will still be a nice constant 12.3 volts at no load. And up to 100 milliamps, we still have 12.3. So we're seeing that now we're in now a much better situation than we were before. The transistor is taking care of that for us. All right. But of course, it has to dissipate up to a certain amount of power in order to do that. Right. So some comments on this before we end is that one, you didn't actually get 12 volts. Right? We wanted a 12-volt design, but we didn't actually get 12 volts, and we're going to have to see how to adjust that in a while. The regulation is okay because it's a series now in addition to the shunt, but we could do something better. What if we wanted 1 amp? What if we wanted 2 amps? And then a bit of a question here. What happens if the load short circuits? We all know in the lab you make mistakes, so you have this running. And if for some reason now the wire coming from this point suddenly touches ground, right? What happens there? A short circuit means that they're going to put 12 volts, 0.3 volts into 0 ohms, right? So you're going to ask this transistor to suddenly have to conduct a huge amount of current. Is going to burn out. If the transistor doesn't burn, the unregulated supply, the diodes or the transformer are going to get very hot very quickly, right? So we're going to have to adjust that now, right? And that's what we're going to look at tomorrow. We're going to start looking. Here is now the full sort of regulator sort of block diagram here. We already spoke about this. So we're going to put in another little bit of circuitry inside of here that is going to help us, first off, keep this even more constant, and then cater for what happens if we do things like short circuit well, in a short circuit situation. And of course here, to be able to set this to exactly the voltage that we want. We wanted 12, we got 12.3. The choice was either to get 11.3 or 12.3. We want 12, right? So we're going to see how to do that. All right. So any questions on what we do, what we did today, before I close off the session? Think about it. As soon as the recording is available, I'll put the link to the recording online so they could listen to it or spot listen. You might want to listen to me for another hour again, but at least go over everything that was said and make your own little notes on this so that you don't have to keep listening over to the whole lecture itself. And then come tomorrow, now we're going to add some more into this. We're going to put in some more components and see how we could make it work a little bit better. Yeah? Make sense? All right. So if you have no questions, let me stop the recording here.